All right, so let's go over the solution for this problem. Hopefully you can all hear me and see me. Can you all hear and see me?
Yes.
Great, thank you, Kat. All right, so for this problem, we're looking at a chemical. It says in the problem statement that it's ethylene, and it gives you values for ethylene from table A1. So it's nice because you didn't actually have to look up table A1, they're already given to you. So we have this chemical, ethylene. Oh, let me stop there. Share screen, advance, content per second camera, switch camera. Right by it. All right. Here we go. All right, so we have this chemical ethylene, and we're told that its temperature critical is 282.4 Kelvin. We're told its pressure critical is 5.12 megapascal. And we're told its R value for its gas constant is 0.2964 kilopascal cubic meter kilogram Kelvin. And these are all coming from table A1 in the book, but they were just given to you in the problem statement. We're also told that the pressure of our system is at 5 megapascal. And our temperature initial, or temperature 1, is 20 degrees Celsius, which is 293 Kelvin. And then we're told our second pressure is 200 degrees Celsius, which is 473 Kelvin. So we have everything that we need to set up the problem, and we're told to use in part A, we're told to use the generalized compressibility chart. Generalized compressibility chart. As you remember, the generalized compressibility chart has the correlation between our pseudo-reduced volume, specific volume, our temperature reduced, our pressure reduced, and our Z compressibility factor. In this problem, we are given pressure and temperature. We're also told information about temperature and pressure critical. So it's pretty obvious that we're going to use our temperature and pressure to use this compressibility chart. So we have our reduced pressure, which is going to be our pressure over our pressure critical. And we have our reduced temperature, which is going to be our temperature over our temperature critical. But for this problem, we have two temperatures. So we have two different conditions. So we're going to have our temperature reduced 1, and we're going to have our temperature reduced 2. These equations are also given at the bottom of in this little chart on your generalized compressibility chart, which is pretty nice. So for our pressure reduced, we know that we have a pressure of 5 megapascal. And our pressure critical is 5.12 megapascal. So therefore, our pressure reduced is going to be 0.977. I'm going to make sure. For our temperature reduced, we have our temperature at 0.1, which is 293 Kelvin. And then our temperature critical, which is 282.4 Kelvin. So this gives us our initial reduced temperature of 1.038. We have our temperature 2, which is 473 Kelvin, over our temperature critical, which is 282.4 Kelvin. As you can tell, these critical values are specific to this substance. They're not specific, they don't change the way that our temperature and pressure do. These are always going to be the critical values. So this value is 1.67 as our temperature reduced 2. So now we can determine our Z value for our initial, so our Z1, and we can determine our Z value for our final condition, our Z2, using the generalized compressibility chart. So on the generalized compressibility chart, we know that we have a pressure reduced of 0.97. So 0. Let's go about halfway, and then another quarter of the way, probably about 9 right here. And then if I'm looking at my lines on the chart, you can see there's a V sub R here, so a pseudo-reduced specific volume going this way. But we're not using pseudo-reduced specific volume for this question. We're using our temperature reduced, or T sub R. So I know that my pressure reduced is about right here. I know that my temperature reduced is about 1.05, maybe a little bit less, but I'm going to say that it's approximately 1.05. So I'm going to draw up from here. I say that we connect about at this line about right here. I'm going to follow this over to the Z value, corresponding Z value on the y-axis, and I get my Z value to be about right here. When I look at this, that looks to be about 0.62, 0.63, maybe a little bit less, maybe a little bit more. So my Z value for my first initial condition is 0.62. So for my second, I'm at the same pressure. I have the same reduced pressure, but this time my temperature reduced is 1.67. So now I'm going to use the 1.6 line, maybe a little bit higher. So I'm going to have this same thing go up to about 1.6. Here I am. Then I'm going to come over to my corresponding Z. All right, I'm about right here. So when I look at what that is, that's about 9.94, 0.95. Maybe a little bit less, maybe a little bit more. So 0.95, what I'm going to put for my second Z value. So as you can recall from the earlier lesson, our Z value is a correction factor for the ideal gas equation. So we've used it several times now. We can use it to correct for our ideal gas because this is not actually an ideal gas. So we can use this Z value to correct for our ideal gas equation. So our ideal gas equation is PV equals nRT. But for this class, what we've been doing is we've been including this mass unit as part of our volume. So P specific volume equals RT. That's our ideal gas law. And this correction factor, this Z, we just include into this equation. So therefore, we have PV specific volume equals ZRT. When it is an ideal gas, Z is 1. So it kind of falls out of the equation. So this ideal gas at 0.2, or this gas at our second condition is going to be acting pretty close to an ideal gas. This isn't a huge correction that's occurring. All right, so now that we have this equation, in the problem statement, we're asked to determine the change in specific volume. So we have our specific volume at 0.1. We can have our specific volume at 0.2 with our Z values at 0.1 and 0.2. And we have our pressure because we're given pressure. We have our Z value at 0.1 and 0.2. We have our R gas value because we were given it in the problem statement from table 1. And then we have our temperature 1 and our temperature 2. So we have everything that we need to solve these equations. We can plug and shove. All right, so for our specific volume 1, this is going to be equal to Z1 R T1 over P. I'm just rearranging this equation. My Z1 value is going to be 0.62. My R value given in the problem statement is 0.2964 kilojoules per kilogram Kelvin. My temperature is 293 Kelvin. and my pressure is 5 megapascal or 5 times 10 to the 3 kilopascal. So solving for this, we get 0.011 cubic meter per kilogram for our specific volume at 0.1. So Noah and Pat, we still haven't answered A yet. We're still working on it. It's a long problem. All right, so specific volume at 0.2 is going to be our Z at 0.2, our T at 0.2 over the pressure. So same thing, just our different Z value or different temperature value. So this is 0.95 times 0.2964 kilojoules per kilogram Kelvin times 473 Kelvin over 5 times 10 to the 3 kilopascal. So only our temperature and Z values have changed between these equations. And this is going to be 0.027 cubic meter per kilogram. We are asked to find the change in specific volume, so our delta specific volume, which is going to be our specific volume at 0.2 minus our specific volume at 0.1. So 0.027 minus 0.011 cubic meter per kilogram, which gives us about 0.016 cubic meter per kilogram for our part A. All right, so that's our part A. And part B, you're asked to compare your result to that obtained using the non-corrected ideal gas law. So for part B, we know that we have our specific volume at 0.2 minus our specific volume at 0.1 over our specific volume at 0.1 times 100 is going to be our change in volume. So our observed minus our actual over our actual, or just this is just kind of a difference equation. And this is going to be our 0.027 minus 0.011 over 0.011 cubic meter per kilogram. So times 100, the units cancel out. This is going to be about 146%. The solution on the solution manual says if you use the ideal gas law, that's an if, sorry, that was bad. If ideal gas. So if an ideal gas, the specific volume is going to be roughly equal to the temperature, or it's not equal, it's going to be related to the temperature. So this change in specific volume is going to be directly correlating to the temperature. So then this equation can also be correlated to our change in temperature over our initial temperature, which is our temperature 2 minus our temperature 1 over T1. These are correlated, directly correlated. So since we don't know about the specific volume of our ideal gas, we do know about the temperature if we assume it's an ideal gas. So then we can just say that our temperature change here is 20 degrees or 473 Kelvin minus 293 Kelvin over 293 Kelvin. And so this is 180 Kelvin over 293 Kelvin. And so this gives us, if we multiply this by 100, this gives us about 61.4%. So this is what the solution from this question, I think this is one from the back of your book, if not another textbook. This is how they answer this question. If I were asked this question, compare your results to that obtained using the non-corrected ideal gas, I probably would just try to work the ideal gas equation again, right? P equals nRT, P equals nRT. And you might need to look up the specific volume from the back of your textbook or something. So I don't think I would ask this question. I haven't really gone over that these are directly correlated, these concepts, whatever, and I would make it a little easier for you. But this is the solution in the textbook. It's a good learning moment. There you go. So any questions?
Basically, that percentage is represent what? Is that an error, or is that, I mean, what is it exactly? Does it?
No, this is your like volume change that's happening from your initial to your final specific volume, and this would be your same corresponding volume change because based on the ideal gas law, the specific value is directly correlated to temperature. Because if we look at P specific volume equals RT, R is a gas constant and our pressure for this problem is the same. So these have to be directly correlated. So our specific volume is roughly going to be changing exactly the way that our temperature changes. And since we don't have any information about specific volume as an ideal gas, then that's why we use temperature here. So Noah's question was, where did this equation kind of come from? And this is an equation we've been working with over the past 2 weeks. But if we look at this, if we look at the basic ideal gas equation, PV equals nRT. This N value here is representative of the amount of moles, the mass of the substance that's there. So if we were to do PV over N equals nRT over N, this N cancels out here. Pressure is an independent variable. It doesn't matter how much mass there is. Well, that gets a little complicated. We don't include pressure per a mass unit because pressure is kind of already an inherent intrinsic value. So this pressure really becomes, or this mass term really becomes related to volume, which is why this is now volume per unit mass, which becomes specific volume. So essentially we've just hidden this mass term inside our specific volume. And then Z, the definition of Z is it's a correction factor for an ideal gas. So it's called a compressibility factor. It's also a correction factor. So it's a correction factor for this ideal gas. Z, the definition of Z is the volume, specific volume over the specific volume ideal. And we also can use it to correct for the ideal gas law, where Z is equal to the specific volume of pressure times pressure over RT. These are definitions like from the book and what Z is. So since we can use Z as these two equations, if we were to rearrange this Z here, we get P specific volume equals Z RT. And so Z here is acting as a correction value for a specific gas that's not an ideal gas, and that's where this equation comes from. So it's just this specific volume is hiding our N term, and Z is not replacing the N term, Z is just acting as a correction value for ideal gas. Okay, other questions?
Will specific volume always be measured in meters cubed per kilogram, unit-wise?
Will
Slide the
specific
sheet,
volume
please.
always be cubic meters per kilogram? What?
Right. Yeah.
Slide it.
Like specific.
In the back of the book, yes, it will. Sometimes you might see it as like liters per liters per kilogram. You could possibly see it as like gallons per kilogram or something, but typically and for an exam, I'll give it to you as cubic meters per kilogram.
Okay.
Other questions? Then we are going to come back to this, and you're gonna work on problem 2. So this is using English units. If you don't have a book that has the E tables, like table 1A or A1E, please, you can look it up online. Just Google like English units table, property tables. But for A1E, you're already given your pressure critical R and temperature critical. So you really just need to use the tables to look up to determine what sort of phase you're in. Are you superheated vapor, or are you a saturated liquid vapor, etc. And then to do some comparison. So you should be able to find these tables on Google if your book doesn't have English units. All right, so we'll work on this for probably like 10 minutes until 12:35, and then I'll go over it for the last 10 minutes of class. Why did we just get 2% for B and not a cubic meter per square life? So for B, if you know that there's 145.5% change in your volume for your corrected, and you know there's a 61.5% change in your volume for your uncorrected, you can just multiply those by your initial volume to determine like the percent change, but we aren't told an initial volume. So that's why we aren't given a volume term. We're just told like the percent change in the volume. We could look it up from the property tables and determine like what sort of initial starting phase this is, and then multiply it by these percentages and then give a volume term. But since we weren't told to give it any certain term here, then I think that this is like an acceptable way of doing it. On an exam, I would tell you, like, give it to me in a percentage or give it to me as a cubic meter per kilogram. But once again, I'm not going to be asking a question like part B on an exam because I think it's a little too like esoteric and ill-defined. Okay. So let's work on number 2. I'll go over it at 12:35. There's only 5 minutes left in class, so I'm gonna go ahead and start going over this. All right. So we have this chemical, and we're told that pressure is 160 psi. Our specific volume is 0.33479 cubic meter. Nope. Trying to go too fast. Cubic feet per pound. These are crossed out. And we're told that we want to find temperature. And first we want to find temperature using the ideal gas model. So that's pretty easy, right? P specific volume equals RT. Rearranging for temperature, temperature equals P specific volume over R.
Yeah, ours should be 0.1052. Problem number 2.
Wait, did I write something wrong?
Oh, should be 0.1052. You do number 2, right?
For number 2, I have 160 psi and 0.3479 cubic feet per pound. What did I write wrong?
I'm talking about the R. Is that the R you write? 3479?
P specific volume equals RT. So temperature equals P times specific volume over R. Okay. So now I have my everything I can solve because I'm given pressure in the problem statement, I'm given specific volume in the problem statement, and I'm given R in the problem statement. So here I have 160 pounds per square inch. I have 0.3479 cubic feet per pound. And my R value given in the problem is 0.1052 pounds per square inch, cubic feet, pounds, ring time. So these pounds per square inch cancel, my cubic feet cancel, my pounds cancel. I'm left only with a temperature term, which is what I want. So solving this, we get 529.13 degrees ring time. This is an English unit. And I would never ask you to use this on an exam, but it's good practice. So if we convert this to Fahrenheit, that's 529 minus 459.67. So our temperature is roughly 70 degrees Fahrenheit for part A. To use the property table, we go to the back of the book. And Zach, can I borrow your book?
Sure.
All right, so I'm going to go to the back of the book. I'm going to look here in my property table. I have my saturated refrigerant. I know that my saturated refrigerant is at 160 psi, so I'm going to come here, 160 psi. My specific volume for my saturated liquid is 0.014. My specific volume for my saturated vapor is 0.29. I'm told in the problem statement that my saturated volume is 0.35. So therefore, my specific volume is larger than my saturated vapor, which means that I'm a superheated vapor. So for part B, my specific volume given in the problem statement is larger than my specific volume of my saturated vapor, which says that I'm a superheated vapor and I need to use table A13A. Or E, I'm sorry for English units, A13E. So now I can go to A13E at 160 psi. I'm going to find my specific volume of 0.379. I'm going to follow this over, and I get 160 degrees Fahrenheit. Yeah, Leila.
Okay, just that again, I'm sorry.
Say that again?
What was the page again, like you were just?
Oh, I'm sorry. This is table A13E. It's on page 953. and I was at 160 PSI. And then I found my specific volume given in the problem statement. Found it that the saturation temperature at in the system is 160 degrees Fahrenheit. All right, so now I know from my property table that my temperature is 160 degrees Fahrenheit. And for part C, I want to find my Z value so I can correct my part A up here. I want to find my Z value so I can correct my part A. So I have my pressure reduced is equal to my pressure over my pressure critical, and my temperature reduced is equal to my temperature over my temperature critical. My pressure is going to be 160 PSI over, I'm given in the problem statement that my pressure critical is 588.7 PSI. So my pressure reduced, the first table was A12E, that's my saturated refrigerant table, that's the table I use to compare. Okay, so this is roughly 0.27 for my pressure reduced, and my temperature reduced is going to be 160 degrees Fahrenheit plus 459.67 to convert to Rankine, whatever. And I know that my temperature critical is 673.6 degrees Rankine. So then this gives me a value of about 0.92. So here's my pressure reduced, here's my temperature reduced. I can take these to the table and get my Z value. So my pressure reduced, which is unitless, so it's nice, I'm going to go to 0.27. 0.2, go about halfway, go 2 more over, 0.27. And then my temperature reduced is 0.92. So I'm going to find my 0.9 line. I'm going to go up to my 0.9 line. My 0.9 line. I'm going to come over to my Z value. I'm going to be about right here. So that's about 0.87, 0.88, 0.86. The solution in here says 0.87, so that's what I'm going to go with. So my Z value is 0.87. So now I have a correction to use for the ideal gas that I used in part A. So remember in part A, my ideal gas equation, temperature equals pressure times specific volume over my R value. So remember pressure specific volume equals ZRT. Isolating for temperature, temperature equals pressure specific volume Z over R. I have already calculated this in part A to be 529 degrees R. And I can just correct it by dividing by this Z value that I found, which gives me a temperature of 608 degrees R. So 608 minus 459 gives us roughly 148.5 degrees Fahrenheit. So if we look, the ideal gas told us that it's 70 degrees. Our property told us that it's 160. So this is our actual value that was measured in a lab. This is what we guessed it was from an ideal gas. You can see that these aren't close to each other. When we use a generalized compressibility chart and correct our ideal gas, we get much closer. So instead of being 90 degrees off, we're only about 12 degrees off. So this is again proof that the generalized compressibility chart is much better at approximating your actual value. All right, so sorry I think I went a little bit over time, but I tend to end class early, so we're not actually over the class period.
Professor?
Let me know if you have any questions. And these are posted on Canvas as a note on Canvas. Under the course module for this week, I have these solutions posted here, in class activity solution here. And then there's also this additional example of using generalized compressibility chart. And this woman goes through an example of using the generalized compressibility chart. And I found it pretty helpful. So if you're still confused, please make sure to watch that. And I hope you have a great week. Wait, why did you use those values? They don't match the variables. Could you put the solution back up?
Yeah, like for that equation right there at the end, I don't understand why you plugged in a temperature and the z value if we had all those variables in the equation.
So in part A, we solved this equation. In part C, we just added a z variable here to correct for this equation. But since we already solved for this, I was just taking a shortcut in time. You could go through and replug in 160 times 0.3 divided by 0.12, but I already know what that value is going to be because I've already done it. So I was just taking a shortcut here and saying like, I've already calculated this in part A. So I'm just going to plug in what I already calculated from part A. Does that make sense?
Okay, so you're just dividing the value by z then.
Yeah, so the only thing I didn't calculate was the z value down here on the bottom. And the z value is here because of its placement in the ideal gas. So you still have this value here uncalculated. I was trying to take a shortcut because I'm really short on time. So I was just saying, I already calculated this in part A. I know what it is. I'm going to keep my z value where it was. Bada bing, bada boom. There we go.
All right, yeah, no problem. That makes sense now.
Okay.
Thank you.
Well then, everybody have a great weekend.
Thank you.
Thank you.